Hello world and hello maths fans. Today we will be talking about exponents and logarithms. We'll first see exponents in the form of order of magnitude estimates when using the technique of Fermi estimation. We'll then look at the rules of exponents. When do we add them, subtract them, and multiply them? We'll then derive logarithms and see how they are the inverse of the process of exponentiation, and in particular, how to derive the laws of logs. We'll then combine everything we've learned about exponents and logarithms to look at fractional and irrational powers, concluding with a calculation of pi to the power pi. Finally, we'll end with an example of applying exponents and exponential functions to economics. In particular, we'll compute the rate of inflation in the fictional Kingdom of Hyrule from the Legend of Zelda video games. But first, let's talk about barrels. let's begin with a classic estimation problem, but with a slight twist. So normally, you might be asked how many sweets are in a jar, but I'm going to do things a little differently. I'm going to ask how many barrels are in this jar. So I'll put that one on the table, and I encourage you to think about or write down your estimate. Second question, how many barrels are in this jar? And again, I encourage you to think about or write down your estimate. Now, what if I were to tell you that the larger jar contains exactly twice the number of barrels in the small jar? I imagine that is probably quite surprising. And this hints at the difficulty that we often see with estimation problems. Our intuition alone is usually not enough to be able to get a grasp of a problem. So I'm going to introduce to you a technique for estimation problems, a series of steps, an algorithm, if you will, that we can use to try and help us when it comes to estimating solutions or answers to a particular question. And this is a very helpful thing to be able to do, because if you're working on a complex problem with many pieces, having an idea of what the answer could be helps you to check that you're on the right track once you begin that very involved process of trying to get to the solution. So one way that we can do this is, and we'll focus here on the small jar to begin with, is by breaking down the problem into smaller or more manageable estimates. So asking how many barrels are in the entire jar, it's quite difficult. It's three-dimensional. It's a bit tricky. There's a lot going on, a lot to process. So what we can do instead is say, well, if we kind of reduce this into two smaller questions. So we could say, well, how many how many layers of barrels can we see? And if we kind of turn it that way, how many barrels fit in a single layer? So those are both much easier things to estimate or to guess when looking at the object. So for the first question, how many tall, I'd say there's about 5, right? It's not going to be perfect, but even if you rotate it, it's approximately 4 to 5 barrels tall. And then if we look at the bottom and think how many barrels fit together in one of those single layers, then again, it's like 4 to 5. So I think as an estimate, we could say, well, let's call it 5 times 5. It's something like 25 barrels. So let's see how close we are. So I'm going to pour these out. We'll count them, just so you all know I'm doing this properly. There is no magic happening here. Let's see how close my guess of 25 is. So we've got there, that's one set of 5. That's another set of 5 for 10. That's a third set of 5 for 15. That's a fourth set of 5. And then we've got 3 remaining. So I make that 23 barrels. So OK, not perfect. I said it was 25-ish. But, right, pretty close. We would be happy with that kind of estimate. And now for the larger jar, we can do something similar. Now, if you remember, I said there was exactly twice as many barrels in here. So we expect, well, we know the answer is 23 times 2 is 46. But would this breaking down approach, this estimation approach, would this work here? So if we follow the same 2 steps, you say, OK, how many tall is it? Well, it's actually about the same height as the original one. And 5 worked well there, so let's call it 5 tall. But what we're seeing with the larger jar is there are a lot more barrels on that bottom section. You can fit a lot more barrels into like one of those 1 layers that we stack on top of one another. So I make that there's sort of like 9 to 10-ish barrels that you can see there at the bottom. So again, that's going to give us 45 to 50, and the answer was 46. So this idea of taking a complex problem, breaking it up into manageable chunks. So this is an estimation technique, which is called Fermi estimation. And again, the idea is complex, difficult to think about problem, often with more than just 2 pieces. There could be multiple pieces, seemingly unanswerable problem perhaps. And then you say, well, can we break this down into these smaller manageable chunks where we have a better chance of estimating each piece, and then we put them all back together and like kind of hope that any small discrepancies cancel out. So it's not a perfect solution to the problem, but it is really very effective, especially if we just want a ballpark figure for what the solution might be. So Fermi estimation is actually named after an Italian-American physicist, Enrico Fermi. He was a Nobel Prize-winning physicist who was working at the University of Chicago in the 1940s. And he used to test his students with these seemingly unanswerable questions. And the most famous, I think, of all the Fermi problems is he asked his students, how many piano tuners are there in Chicago? Now, in the modern day, we could ask the same question, but we could probably just search online to get the solution. So I want something that's potentially unanswerable to demonstrate this Fermi estimation technique. So the question we're going to answer is how many barrels has Donkey Kong thrown in his entire career? So this is why we were working with barrels rather than sweets. And just to clarify why we are talking about barrels and Donkey Kong, so Donkey Kong is the, let's say, nemesis of Mario in some of the Super Mario games. The original Mario game, Donkey Kong was kind of at the top of a series of levels. I think it was meant to be a construction site, and Mario has to climb up all of these ladders and get to the top. And Donkey Kong is trying to stop him by throwing barrels that roll down through those layers. So the question is, given the video game setup, how many barrels has Donkey Kong ever thrown over his lifetime? So we'll answer that by going over to the screen. But we'll begin with a just formal sort of statement of the Fermi estimation technique, and then we'll use those steps to try and answer our question about Donkey Kong and his barrels. So Fermi estimation is formally the process of estimating the solution to a complex problem by breaking it down into its component pieces, which are much easier to estimate. And usually here, we estimate those smaller pieces to the nearest order of magnitude. And what we mean by order of magnitude is basically powers of 10. So 10, 100, 1,000, etc. Step 1, given a question like Donkey Kong and barrels, we break it up into those manageable pieces. So again, for our jar example, rather than the whole jar, we said, well, let's look at the height and the base. We then provide order of magnitude estimates, so again, sort of to the nearest power of 10 of each piece. So what feels like the right kind of value. And then step 3, we combine all of those pieces to get our final estimate to that original question. So on to Donkey Kong and barrels. So in order to answer this, we're talking about how many barrels have been thrown. And I think a couple of things that we need to think about are, well, how long has Donkey Kong been doing this, right? So there's like a time element. And then there's also a rate of barrel throwing. So in the game, like how often is Donkey Kong throwing or destroying a barrel? So that might be our first question. At what rate is Donkey Kong DK throwing those barrels? And then if we know that rate, then we could say, OK, so we know the rate that he's throwing barrels. We'll try and estimate that in a moment. Then, well, how long are those games being played for? So if he's throwing the barrels at some rate, but how long is he doing this? And that just means, well, how long do people play the game? So we might say, well, you know, how long is each game played by the person doing the playing? But then for someone to play the game, they have to purchase the game in the first place. So now we might say, well, OK, then, so how many games have been sold? Right? So how many copies have been sold of each Donkey Kong game? Which then tells us sort of the final question we need then is, well, how many games are there? Right? There's not just one original Donkey Kong game. There are several over the last 40 years. So if we can now estimate each one of these questions, estimate an answer to each one of these questions, then we can put them all together by multiplying and hopefully get our answer to this seemingly unanswerable question. So at what rate does Donkey Kong throw barrels? Now this requires a little bit of knowledge of the game, or perhaps some assumptions about how the game is played and what happens. So I do remember playing this when I was a lot younger, and to me it's kind of like every few seconds there's a new barrel coming down. And we don't need exact answers here, right? We're estimating. So every few seconds there's a barrel. Maybe there's like 20 a minute. So if it's 20 barrels per minute, then across an hour, that would be 20 per minute multiplied by 60 minutes in an hour. So 2 times 6 gives me 12. carry the two zeros, that's 1200, 1200. But this is a Fermi estimate, so we go to the nearest power of 10 order of magnitude, so that would be 1,000. So we'll say there's approximately 1,000 barrels per hour of non-stop barrel throwing from Donkey Kong. So then how long do you play the game? So again, if we just think about this order of magnitude concept, well, 1 hour feels too low, right? If you're going to go out and purchase the game, you're going to give it at least an hour. But then there's going to be many, many people who will play this for multiple hours, right? If you think generally how long do you play a game, it's probably more than an hour. But then going up to something like 100 hours feels too long, right? It's unlikely you are going to devote 100 hours to a Donkey Kong game. Not against it, but it feels like it might be more of an extreme example. So something in the middle, right? So 10. 10 feels about right. So let's say we've got 10 hours, 1,000 per hour. So we're kind of building up our solution here at the bottom. So 1,000 barrels per hour multiplied by 10 hours. How many copies have been sold? So again, this requires a little bit of knowledge or assumptions about the video game industry. Like typically, we're talking millions. If you think about popular games, right, that's why they enter popular culture, and most of us have heard of Donkey Kong. So let's think like we've got like a 1 million, a 10 million, or 100 million. So like 100 million feels like excessive for a single title. Like some games reach it, but not, they are like the best sellers of all time. So 100 million feels too much. 1 million feels maybe a little bit small, like given how popular Donkey Kong and well-known Donkey Kong is. So again, let's go with 10 million. So 10 million, just to write that using our order of magnitude or our powers of 10 notation. So a million has 6 zeros, which means it's 10 to the 6. So therefore, 10 million is going to give us that 10 to the 7. And then finally, how many Donkey Kong games are there? So again, if we think about this through order of magnitude, there's definitely more than one, and there's definitely not 100, right? So it's going to be 10. The exact number is kind of irrelevant here for the estimation. We just know it's not 1 and it's not 100, so it's an order of 10 guess. So now we've got our answer. So we multiply all of these numbers together, and we're going to get an answer of how many barrels has Donkey Kong ever thrown of 10 to the 12, or 1 trillion. So perhaps not the most useful piece of information you have ever heard or ever learned, but the process of getting to that estimate using Fermi estimation, breaking down complex problems into more manageable pieces is incredibly helpful and incredibly important. What is an exponent? Let's look at the definition. So an exponent is just repeated multiplication. So it's a shorthand way to express that we have some value, some number, and we just want to multiply it by itself several times. So for example, if we've got the number 2 and we do 2 times 2 times 2 times 2, then we can write that. There are 4 2's there, so we just use an exponent to help us display that information. So that's just 2 to the power 4. We can also do this algebraically, so we don't need to yet define our base is that 2, so we can say it's a times a times a, 3 lots of this number or variable a, so that's a cubed. And as I said, the number that we use at the bottom, the number being raised to the power, is what we call the base. So here we've got base 2 to the power 4, and here we're using base a to the power 3, or we would say exponent 4 or exponent 3. Now, common bases you'll see are things like the number 2, especially when working in binary, in computer science, and also 10, because we work in the decimal system with our own numbers. Now, exponents can be positive, as we've seen. So, for example, 2 cubed, which means 2 times 2 times 2, would give us 8. But they can also be negative. So if we have a negative exponent, then what that is telling us is actually that we are dividing by that number. So 2 to the negative 3, 2 to the power of minus 3, actually is just meaning we do 1 divided by 2 cubed. And then 2 cubed, or 2 to the power 3, we just expand and calculate as we just did before. So 2 cubed is 8, so 1 over 2 cubed is 1 over 8, or 1/8. So we've got positive, we've got negative, so we also have 0. Now 0 powers, any real number to the power 0 always gives us 1. So this is a helpful thing to remember and a very important rule when it comes to powers and exponents. So 2 to the power 0 will just give us 1, but again, any base to the power 0 will give us that 1. So we've seen their examples base 2, so let's look at some examples base 10. And in particular, an important term is something called the order of magnitude. And this is just giving us an idea of the size of a particular number. So formally, we can say the order of magnitude of a number is the exponent of 10 when we write that number in scientific notation. But as I said, colloquially, it's just a nice estimation for how big a number is. So we'll be working with the tens, the hundreds, the thousands, the millions. It's helpful to know the size of the number we're working with. That's when we might use the term order of magnitude. So for some examples, using actual scientific notation, so the number 11, to write in scientific notation, we just change that to something multiplied by a power of 10, where the something is between 1 and 10. So 11 becomes 1.1 times 10 to the 1, so we would just say its order of magnitude is order 1 or is 10. Then for 314, so that in scientific notation would be 3.14 times 10 squared, so it's order of magnitude 2 or order of magnitude hundreds, order of magnitude 10 squared. You can use all of those terms. And 0.123, so this is now a number smaller than 1, getting into the decimals, so this will be 1.23 times 10 to the minus 1. And again, this is telling us we're working in the tenths, so our order of magnitude is 1 over 10, or 10 to the minus 1. Okay, so positive, negative, orders of magnitudes, lots of things going on with those powers, but we also can combine them. And it's important to be clear on how we combine them. So when you have two numbers which both have the same base, and this is very important, so as long as you have the same base, it's a, base a to some power, right? That could be 2 to some power, multiplied by the same base, so a to a different power, or 2 to a different power. So when you multiply those numbers, you add the exponents. Okay, so multiplication of two separate powers or two separate exponents gives you a final outcome, same base, but we add those exponents. Now when we divide two exponents or two powers of a number, again we need the same base to be able to do this, but if we have a to the m divided by a to the n, so we can rewrite that in fractional form for that division. And now this helps us if we think about what our negative powers meant. So the power on the bottom, we just saw, that means the negative power on the top. So a to the m divided by a to the n is actually just a to the m multiplied by a to the minus n, and then we combine them like we had above. So when you're dividing, you subtract those two powers, and we can see there, once we have our definition of negative powers, we can see how to get this subtraction using the first rule at the top of the screen. Now, the other one to be aware of is when you have a power raised, or a number to a power raised itself to another power. So here, for example, a to the m to the power n. So what that is telling you is that we want to multiply those two numbers together. So for example, if you had 2 cubed and then you're squaring that whole thing, then you can say, well, that's 2 cubed multiplied by 2 cubed, and so that's 2 to the 6. But we can see here it's the same as being 2 cubed to squared, 3 times 2, to give us that a to the power of m times n. So let's go over now and look at some examples with actual numbers. So the first one we might have here, I'll do something algebraic. So let's suppose we kind of combine all of those rules together. So what if we have something like a multiplied by a squared, then we take that entire term to the power 3, and then we divide the whole thing by a to the power 12. So we've got there all 3 of those rules I've just mentioned, all kind of combined into a single term. And let's see if we can simplify this into a single final power or exponent of a. So the first thing we might do is do the multiplication inside that bracket on the numerator on the top of our fraction. So we've got there a to the 1. And I'm just going to add in a 1 there just to make this really clear. If you have a single variable or a single number, that means it's to the power 1. So when you multiply that by a squared, a to the 2, we add those two powers. So that term in the bracket is just going to become a to the power 3, because 1 plus 2 gives us the 3. We've then still got the 3 outside, and we've still got the 12 on the bottom. Now let's simplify the number on the top, the numerator. So this is now an example of that third rule, where we have an exponent itself to a certain power, and we multiply those two numbers. So it's very important that you're careful here with which rule applies in this situation. So we've got a to the 3, all to the power of 3. 3 times 3 gives us 9. So the resulting power there is going to be a to the 9 divided by a 12. And then finally now we can use that second rule about division, which becomes subtraction. So we know that that's just equal to a to the 9 minus 12, following that rule, which then gives us a to the minus 3. And we could leave it like this. This is completely correct. But I like to kind of always have a positive number. So I just like to turn that into a nice fraction so we can see it's 1 divided by a to the power 3, or a exponent 3. OK, look at another example. So now let's suppose we're going to add some powers, which is something we haven't yet seen, but we have enough information to be able to think about how this works. So if I have a squared plus a cubed. So we've looked at the rules of how to manipulate powers when you're multiplying them. But now we're looking at adding them. And the key thing here is that we can only actually add those first two. So when we have terms of different powers, we can only add them if they have the same power. Right? So a squared plus a squared. I've got one lot of a squared. I have another lot of a squared. I've got 2 lots of that thing. So I'm going to get 2 lots of a squared, and I have to leave the a cubed alone. Right? I cannot add that in. That's a separate, different term to the first one. So that's the only simplification we can actually make with this particular equation, this particular example. And now a final, very computer science related example. Let's suppose that we have a program that we are coding up, that we're running, and it has n steps. So there are some number of steps based perhaps on a number of inputs. And then we're going to actually have this program. It's going to be nested 3 times, or triple nested. So sort of one inside the other inside the other. And so what that would mean is that we're running it n multiplied by n multiplied by n. And so the overall runtime, or the overall power of what we're seeing there, is going to be n to the 1 times n to the 1 times n to the 1, and we add all of those powers. So that would be n cubed. But now if we did the same kind of problem, the same kind of idea, but what if the program we're running, rather than being n steps and order n, what if it was n squared? So again, we still have a nested 3 times, but maybe we now have n squared, and that is now nested 3 times. So there's 2 ways we can think about computing the final exponent of this program. So we could do n squared multiplied by n squared multiplied by n squared, similar to how we thought about that initial n times n times n. And that would give us, again, following our rules, that gives us n to the 6. Or we could say, well, I know that running it once is n squared, and we're just going to execute that 3 times. So we can write it as n squared to the power, or exponent 3. And then our third rule of powers, rules of exponents, gives us n to the 2 times 3, which of course, fortunately, gives us the same answer, n to the power 6. So a few different examples there of using those rules in practice. Now there's a couple of other important properties and let's say relationships with powers that we just want to be aware of. And I thought I would just kind of address a very important and common misconception when talking about exponents and exponentials, because these are very, very similar words. And so it's very important you're clear on the difference between those 2 things. So if we look at a function, or an example of 2 to the power x, 2 to the x, where x here is the exponent. So this we would call an exponential function. And then we call this an exponential function because the variable, the thing that changes, is x, and that variable is in the exponent. Right? So the power here, the thing we're raising 2 up to, the x here is our variable. So the power itself is what's changing, so we call that an exponential function. But it's important to see that that is different, very different, as we'll see in a moment with the graphs, to something like x squared. So x squared is a polynomial function. It is a power of x. And here, what we've got is this has a fixed exponent. So the 2 here does not change, right? We can change x, we can change the number that we are squaring, but we are always squaring it. We are always having a fixed exponent of 2, whereas again, in the first one, the exponential function, we are changing the exponent. So you want to be clear on exponential functions have the variable at the top, whereas something like a polynomial function, exponent 2, is saying that the power, the exponent, is fixed, but we're varying the base, or the number at the bottom. And we can see this very clearly if we look at their graphs. So here we've got x squared shown in the orange color, which is this U shape, versus 2 to the power x, which is shown in blue. So we can see the x squared has this nice symmetry passing through 0, whereas the exponential function, 2 to the x, is increasing constantly and passes through 1 when x is 0, because as we've seen, 2 to the power 0, any number to the 0 goes through that point 1. Now an interesting thing with these 2 graphs is if we zoom out and take larger and larger values of x, then we really see the difference in their behavior. So over here, again, the orange is our x squared, and our 2 to the power x, our exponential function, is in blue. So we can see that the blue is just shooting up faster than the orange, and it only does that for the positive numbers. OK, now a final thing related to bases, which is just important to point out. We've seen 2s and 10s and general bases A. But Mathematically, we often talk a lot about the particular base, which is the number e. Now, e is Euler's number. It's an irrational number, so it goes 2.718 ... It continues forever. It is a non-terminating, non-repeating decimal. So that's what makes it irrational. That carries on. And we use this to define something called the exponential function, written exp of x, or e to the power x. So it's the same as what we just looked at with 2 to the power x, except it's just a very specific choice of base. Rather than 2, we use this irrational number e. And by doing this, it has lots of interesting and fun properties. One of my favorites being that at whatever value of x you have, the rate of change, the rate of growth of your function is exactly equal to the value that you're currently at. And there are many other sophisticated properties and things that you can do with this function, which is why it has this special name and this special choice of base. So to summarize, we talked a lot about exponents, but the main point to get across is an exponent is just a repeated multiplication. We also looked at the rules of exponents. So when we multiply, we add them, division, subtraction, all those kinds of things. And we also looked at some examples towards the end of different bases and the importance of an exponential function compared to just being an exponent. what is a logarithm? A logarithm is just the opposite or the inverse of an exponent or an exponential. Let's look at that definition. So, logarithm does the opposite of exponentiation. It is the inverse to raising a number to a power. So this means that taking a log, or the logarithm function, cancels out the exponentiation. So if we have something like log base a of a to the x, the log base a is cancelling out the a and just gives us back that variable x. So we interpret something like log base a of c as the value of x satisfying an equation like a to the x equals c. So when we have something like this, this is saying we have a number a, our base, and we raise it to some power x, possibly unknown, and it's got to be equal to some constant value. So the logarithm here is going to help us figure out the answer to that equation, how to solve that equation. And what you can think of doing here is taking the logarithm base a of both sides of that equation. So we take log a of both sides, the a's cancel out over here to leave you with x, and then our solution to that, our value of x, satisfying that equation, is going to be log to the base a of c. Now, as with exponentiation, we can take different bases. So common bases we'll see are similar values. We use 2 when working in binary. We might use 10 for decimal. But again, that base of the logarithm can be any value. So let's go over to the board and look at some examples. So we'll start with something hopefully familiar, with a question like, what if we wanted to just calculate log base 2 of the number 32? So if it's being asked, what is this? Then the question you're actually being asked, or what this represents, is it's saying what power of 2, what power of the base gives 32? So what power of 2 gives us 32? Well, we think about that. So go 2, 4, 8, 16, 32. So it's 5. So the answer there would be 5. So log base 2 of 32 is just 5. But we can also use logs when we don't know the specific power. So for example, we could have an equation we might want to solve, which is 10 to the power x is equal to 50. So in this situation, again, if you think about what is this question asking, we want to work out the value of x. This is really saying, like, what power of 10 gives us 50? And again, if we think through similar to that first example, we kind of multiplied some 2's together. Well, we go 10 and then we go 100. So like we skip the 50 in the middle. So that's telling us it's not like a known answer. It's not an integer power that we can just immediately recall. And this is where the log's going to help us, because taking log of both sides of this equation, so we must do the same to both sides to make sure it remains equal. But taking the log to the base 10, it's going to bring down that x. So it's going to cancel out that exponentiation process. So if we do that, we can say taking log of both sides, so log base 10 of 10 to the x, well, that just cancels out the 10's and gives us the x. And then having done it to the other side, we then say, well, x, therefore, is log base 10 of 50. Now, this doesn't give us the actual decimal answer. For that, we're going to need a calculator. But we now know how to work it out. So the solution is x equals log base 10 of 50. And we can kind of have a feel for what that value might be. So 10 is too small, so we know it's bigger than 1. 10 to the power 1 doesn't So let's go over to the board and go through some examples. So we'll begin. Oh. I don't know if that would have been caught, but it threw me, so I'll go again. That's fine. Should I just go again?
Yeah, you're clear anytime, Tom.
OK, thank you. So let's head over to the board and go through some examples. So we'll begin with something hopefully familiar. And we could ask a question like, what is log base 2 of 32? So we want to work out, like, what does this actually represent? What is this value? So what this is really asking us is it's saying, if we take the number 2, what power, what exponent do we raise it to get the answer 32? So we can kind of think this through. So if we have 2 by itself, that doesn't work. So then 2 times 2 would give us 4. We bring in a third 2, that gives us 8. We bring in a fourth 2, that's going to give us 16. And then that fifth 2 gives us 32. So this is 2 to the 5. So 2 to the 5 is giving us the 32. So therefore, log base 2 of the number 32 is equal to 5, precisely because 2 to the 5 gives us 32. So taking log base 2 of both sides is then giving us the answer of 5. Now let's look at one where perhaps the solution isn't an integer, it isn't a known value like that one being a power of 2. So suppose we want to solve something like 10 to the x is equal to 50. So again, this is asking us what power of 10 gives the number 50. So we could begin in a similar way and say, well, we know some powers of 10. 10 to the power 1, 10 exponent 1 gives us 10. 10 squared, 10 to the power 2 gives us 100. So it's between those two, right? So we kind of have an idea that x is between 1 and 2, but we can't just immediately get the answer through that cancellation process. So we have to actually go in and take the log of both sides of the equation to pull down the x. So what I mean by that is if we imagine doing log base 10 of both sides of the equation, and recall we have to do the same to both sides to make sure the equation still holds. As long as we do the same to the left and the right, the equality. So now let's head over to the board to look at some examples. So we'll begin with something familiar in the form of powers of 2. So we could ask a question involving logs, something like, what is the value of log base 2 of 32? So what this is expressing, what this is asking us, is what power of 2 gives us the answer 32. So we can think through our powers of 2. So we go 2 multiplied by itself gives us 4, multiplied by 2 again for 8, fourth time for 16, fifth time. So 2 to the power 5 gives us 32. So if we write that down, then what we can do now is take that and kind of put the 32 inside the log. So log base 2 of 32 is the same as log base 2 of 2 to the power 5. And now we can really clearly see how the log and the exponentiation cancel out. And that's just going to leave us with the answer 5. So the value of log base 2 of 32 is just 5. But what if it's not a known result? What if it's not a power we can immediately recall? So what if instead we had something like 10 to the power x is equal to 50? And what I mean by a power we cannot recall is we might say, well, 10 to the power 1 is 10. 10 to the power 2 is 100. So it's a non-integer power is going to be our solution here. So we don't immediately know what the answer is, and we can't rewrite 50 as a power of 10 immediately like we just did. So here we really do need to go through and take log base 10 of both sides of the expression to kind of cancel out the exponentiation. And it is important we do the same to both sides of the equation to make sure that it still holds true. So we could do log base 10 of 10 to the x. And doing that, we know that the log cancels out the exponentiation, so that gives us x. And then doing the same to the other side, the 50, we know that log base 10 of 50 is going to then be equal to the x that we have. So we know that x is equal to now log base 10 of 50. We've done the same thing to both sides of our equation. But as I said, we can't immediately say what the answer is. And we would need to now use a calculator to plug in this expression to get the answer. But since we know that 10 to the 1 gives us 10, and 10 to the power 2 gives us 100, we expect the answer to be somewhere between 1 and 2. And when you plug that into a calculator, you'll actually get that x is equal to 1.699 to 3 decimal places. So just keeping the 3 decimal places, number carries on, but that will give us log base 10 of the power. I'm just going to do that again, that last bit. But that will give us log base 10 of 50, which is the solution to the original expression, 10 to the power x equals 50. Sorry, I'll just do that last bit again and try not to fumble the pencil. So this gives us, OK, 1.699 to 3 decimal places. So that gives us the solution, the value of x, or the power of 10, that gives us the number 50. So now let's go back over to the screen and look at now some of the rules or the laws of logs. So here, when we have 2 logs, so we've got log base a of some number x, some variable x, log base a of some variable or number y. So when we add together those logs, they must have the same base in order to do this. So it's important they both have the same base a here. But we add them together, we get log base a of their product. So when you add the logs, you multiply the argument. So you multiply the variable or the terms inside the logarithm itself. When you subtract logs, we follow a similar idea. So log base a of x, again, must also have the same base, minus log base a of y. This time we divide the arguments inside the log. So adding them, we multiply. Subtracting them, we divide. And the other one that's really helpful here as a law of logs is when we have a log multiplied by a constant, so we have some number of this particular log, then what happens there is that m, that number outside, becomes a power inside the log. So the number in front, the constant m, becomes a power. You raise x to that power. It becomes your exponent inside the logarithm. Now, these results we're seeing on the screen are actually derived from the way that we manipulate exponents. So let's go over to the board and see how that works. So if we look at the first one, so what we've got here, our first law of logs was telling us how to add them. So if I write that out, it says that log to the base a of x plus log to the base a of y is equal to log to the base a of x times y. So the way to think about this, or show how this is related to powers, is as follows. We begin by looking at the right-hand side of the expression. So if we look at log to the base a of x, y. And what we want to do here is use a very neat trick, which is using the definition of the log itself. So we're going to rewrite x and y in terms of powers. And since we know that logs and powers cancel out, we can say that x is actually equal to a to the power of log base a of x. So I'll just make that a little bit clearer. So a to the power of log base a of x. So again, we've got a to the power of log, so those will cancel each other out precisely because they are inverses. So we know that this is true, and we do the same with y. So we turn y into a power of a. So that's a to the power of log base a of y. Now, using these alternative ways of writing x and y, we can turn the problem involving logs into an expression about powers. So when we now substitute those into our expression, what we can say is, well, this is log base a of, it was previously x times y, but now we've replaced x with a to the log base a of x multiplied by a to the log base a of y. And now the reason this is really helpful is we've got there two exponents, two powers of a multiplied together. So when we multiply together two exponents in this way, we add the exponents, we add the powers. So doing that, I'll just carry on down here, we can say now that this is therefore equal to, we've got log base a, and then in the bracket we add the powers, so it's a to the log base a of x plus log base a of y. And now we cancel out the log and the a to a power. So they kind of cancel each other out, and we're just left with log base a of x plus log base a of y. And just to make that really clear, because they are kind of cancelling each other out, they bring down that power of a. So we started from here, and we ended up here, showing that first law of logs to be true. And as we saw, that was by translating it and using the rules of exponents or powers. Now we can do something similar with the other two. I won't go through all the full steps, but I'll just point out two really important things we can use to help us. So normally we then think about the third of our laws. So the third of our laws of logs tells us that m times log base a of x is equal to log base a of x to the power m. So here, what we can do is take law 1, the one we just showed, where we were adding things together. So we can say log base a of x, and then we just add on another one. So another log base a of x. So this is one particular value. And then following the first law of logs, we multiply x times x. So we know that that is log base a of x squared. So then we can generalize that result to get this is true for any value m. And then to get our third and final law, which is the second one written on the screen, the one about subtraction and dividing, the trick to that one is, well, if we think about what we're trying to consider, we're looking at log base a of x divided by y, and we want to show this is the subtraction of those two logs. So what we just do here is we rewrite the y on the bottom as a -1 power. So again, we convert it using what we know about exponents, and we say that's x, y minus 1. And now using the rule at the top of the screen, that third law of logs, we can then bring down the -1 and then use the result we had earlier and separate it up to get that subtraction. Okay, so a couple more things on logs that are just worth mentioning. Right, we've already covered quite a lot, but there are a couple of other things that are just worth knowing when thinking about logarithms, or that you might see. One of those is what's called the change of base formula. So when you're working with a log base A, and maybe you want to change, you want to work in a different base, then this is a formula, a very helpful formula that tells you how to do that. So if we go from log base A of x, and maybe you want to change to base B, then this is telling us we just have to divide by this constant value. So the term on the bottom is related to A and B, so it's important to know the two bases, the one you start in versus the one you want to get to. So that's going to be a very helpful formula to remember and to use. The other place where we often see logs is with visualizations, with graphs, and displaying data. And we use logarithmic axes, particularly when we want to show something where the values we're using have a really large range of order of magnitudes. So maybe you've got some tiny values, like much smaller than 1, and you've also got some much larger values, maybe up in the millions or the billions. And if you want to show all of that information on one graph, it can be quite tricky. So here's an example of 2 to the power x. So this graph here is 2 to the power x, and as we can see, we get up to about 2,000 in the space that we can fit on the screen. This is a normal set of axes, just with a bigger scale on the y-axis. But if we do this with a logarithmic axis, then what we're doing here is we're putting powers of 10 along the x-axis. So this is going from 0.1 or 1/10, 10 to the -1, 1/10, and then similarly up here. But you can see in the same space, the same visualization, we've got the same shape, but we're actually going here, this is 10 to the 6, which is a million, so we've got here up to 100 million being displayed on the plot. And all of these lines are representing all of the logarithmic axes that are underpinning that particular plot. So they can be very helpful, as I say, for showcasing data across all of these ranges. Now, a final thing to mention in relation with logs is an important base. So I mentioned we usually see 2, particularly in computer science, and binary, 10, of course, talking about decimals and the numbers we're used to using. But mathematicians in particular, we often work in base E, and E is an irrational number. So 2.718 ... it is a non-repeating, non-terminating decimal, so it goes on forever. And we use this to define what we call the natural logarithm. So this is just the log base E. And we often write this, or we do write this, as ln of x. So natural logarithm would be nl, but to emphasize it is a log, we put the L first. So it's log base E ln of x. And this is the exact inverse, therefore, based on how we've understood logs, this is the exact inverse of the exponential function e to the x. So if you take the natural log of e to the x, we get the x back because the natural log cancels out with that e exponentiation. So to summarize, we've talked a lot about logarithms, but fundamentally they are just the inverse of exponentiation. They cancel out the power and bring down the power so we can solve equations. So this can be a very helpful formula to remember and to use. The other place where we might see logarithms is with logarithmic axes. So logarithmic axes are useful when we want to display information, data, equations that cover several orders of magnitude, and we want to show all of that on the same plot. So I've got here an example of one of my favorite graphs. So this is showing the maximum speed of a range of animals. On the left, we've got animals that live on the land, and on the right, we've got the same, but animals that live in the ocean. And what it's plotting is it's plotting the speed on the y-axis versus the size of the animal, their mass, along the x-axis. Now, if you look carefully at these axes, these are logarithmic axes. So rather than the standard way, perhaps, of labeling, of going maybe 0, 10, 20, 30, we have that constant gap. We're seeing here that we're going up in powers of 10. So it's using that logarithmic scale. We go 1, 10, 100, 1,000. And again, the reason this is really helpful is it means we can show something like one of these insects, which have a very, very small mass, like 10 to the minus 6 kilograms, like tiny, all the way up to something like an elephant, which is multiple tons, getting up to 10 to the 6, 10 to the 7. So we can show all of those range of values on the same plots, and we can show this lovely result relating to which animals are the fastest. The final thing I just wanted to mention related to logs, just to round this all off nicely, is something called the natural logarithm. So as we've seen, we can choose a different base for our logarithm. We were working log base a. We can pick a to be any number we want. But one that's commonly used is base e, where e is an irrational number given by 2.718 ... So because it's irrational, that means it has a non-terminating decimal that is non-repeating. So that number goes on forever after the decimal point. And we use this number to define the natural logarithm. So it's just log base e. We write this as ln. So obviously natural logarithm suggests writing NL as shorthand, but to emphasize that it's still a log and it still behaves that way, we just put the L first. And just to really stress the relationship with the number e, if we take the natural logarithm of the exponential function, so natural log of e to the x, they cancel out and give you back that x, so they are the inverses of one another. So to summarize, we talked a lot about logarithms and all their various different properties and use cases, but the most important thing to remember is that the logarithm is the inverse or the reverse process of exponentiation. The most common exponents we see are usually integers, whether positive, negative, or sometimes 0. But we can in fact define any power, any exponent. That includes rational numbers or fractions and even irrational numbers. And here's how it works. So we begin by looking at rational or fractional exponents. And the key thing here is that they are related to roots. So if we start with the canonical example, the square root of x is just written as x to the power a half. So for a square root, the exponent is just a half. And then if we wanted to take a different root, suppose we want to do a cube root, then the cube root of x, where we have a 3 here to signify the cube root, gives us x to the 1/3. So we're seeing here that the number on the denominator, on the bottom of our fraction, in the power or the exponent, that is telling us what root to take. And this pattern continues. So if we wanted the nth root for some integer n, then that just means the power 1 divided by n. So that helps us make sense of the denominator, the number on the bottom. But we can actually now combine these roots with powers themselves. So what I mean is if we have something like x to the power, x to the exponent 3 divided by 2. So the 2 on the bottom is telling us to take a square root. So that means do x to the half. But then we can put the 3 outside using the multiplication rule. So what we end up with, x to the 3/2, is actually just the square root of x cubed. So it's telling you to take the square root and then raise it to the power 3. You can, in fact, do that in the opposite order if you wish. So you could do x cubed, x to the power 3 first, and then square root the whole answer. But again, the fraction is just telling you which operations to use. So let's go and look at some examples just to make sure we're clear with how this all works. So our first example could be something like the following. So let's suppose we have x to the 3/2 power, and let's suppose I'm now multiplying that by x squared. Okay, so in this instance, we have the same base, x to 3/2 and squared. They are being multiplied together, so our rules of exponents tell us to add them, and nothing changes here. We just add the powers. Even though one of them is a fraction, it still works. So we have to do 2 plus 3/2. So what we want to do really is say, well, that's x to the 3/2, and then we want to do plus 2. And then we can rewrite the 2 and say, well, that's actually 2 is just the same here as 4/2. And so therefore, x to the 3/2 plus 2 is in fact just x to the 3/2 plus 4/2. So now we can actually add those fractions together. They have the same denominator, same number on the bottom, so we get x to the 7/2. So that's telling us that that product is actually just the same as square rooting x and then taking the whole thing to the power 7. Now, let's look at the same equation to begin with. Suppose I have x to the 3/2 still multiplied by that x squared. But now, let's take the whole thing to the power of a half. So we just worked out what the inside of the bracket was equal to. So we saw that that was x to the 7/2. And now we want to take that whole thing to the half. So again, we follow the same rules. Just because they're fractions, the rules of exponents don't change. So we multiply those two numbers. So the solution here is x to the 7/2 multiplied by 1/2. We multiply the top and the bottom, so it's 7/4. So again, the answer or solution to this particular expression is the 4th root of x, then raised to the power 7. One final example. So now let's suppose we have x to the 3/2, the one we just had, multiplied by x squared. And again, as we just saw, let's suppose we take that to the half, so we can use our previous working. But now let's divide the whole thing by x to the 3rd. So there's quite a lot going on. Again, we're seeing all three of our rules of exponents combined into a single problem. So we already did the hard work. We know how to simplify the top. We did that in the last two examples. So if we kind of just jump ahead, then we know the top is x to the 7 over 4 from our previous working. And then the bottom now is x to the 1/3. So now having a number on the bottom tells us we are taking away, subtracting the exponents. So that's now x to the 7 over 4 minus 1/3. And now again, we have to do our work with fractions. So we want to subtract two fractions, so we need them to have that common denominator. So 7 over 4. So, and then we want to also compare that to 1/3. So if we multiply 4 and 3, that's going to give us the same common denominator for them. So 7 over 4 is the same as 21 divided by 12, multiplying the top and the bottom by 3. And then 1/3, we can convert that by multiplying the top and the bottom by 4. That's going to give us 4 divided by 12. So now we can go back up here and say, so this is actually just x to the 21 over 12 minus 4 over 12. Now we can subtract them. So the answer is x to the 17 divided by 12. So it's the 12th root of x taken to the power of 17. All right, so that gives us fractional or rational powers. But what if we have an irrational number, a number that cannot be written as a fraction? So there's a very clever way that we deal with this, and that's using logarithms. So it's bringing together those topics. So we define irrational powers using the exponential function and the natural logarithm. So for example, if I wanted to work out x to the power pi, so pi being an irrational number, 3.14 ... going on forever and related to circles. So I want to work out x to the power pi, an irrational power. Then we say, well, that's just the exponential e to the power of the natural log of x to the pi. And that's OK because the e and the log would cancel out. So we can put them in knowing that they don't do anything. And then using the powers, or the rules of logs, I should say, the laws of logs, we bring down the pi in front of this value. And now this gives us a formula and something we can use to actually compute using the exponential function. Now just a subtle note to say, this is generally how we do this. We often will use the natural logarithm and e as our base. You can actually do this with any base, but just for kind of convention, we usually do it this way. So now we have a way of making sense of x to the pi, so let's figure out some values. So for example, if we set x to be 2, then using this formula, we can say, well, 2 to the power pi, very interesting number to think about, is, according to our formula, e, this exponential function, to the power x to the power pi times the natural log of 2. Now we can work out all of those pieces, plug everything in to a calculator and get it's about 8.824. And we can do my favorite example, which is pi to the power of pi. It's the same formula. We just replace the x with a pi. Again, this is now, all of these things can be very easily computed and thought about using the logarithm function, the exponential function. And we get the pi to the pi is a little over 36. And my favorite fact about both of these numbers is we don't actually currently know if they are irrational. We're pretty sure they are. They look like they're irrational. The decimal, we can calculate more and more places of the decimal, but we don't actually know for sure that they are irrational numbers. We don't know for sure that that decimal is not repeating and non-terminating. So to summarize, we've now seen how to compute fractional or rational powers using roots. And for irrational powers, we define them using the natural logarithm and the exponential function. Since exponents refer to start that one again. Okay. Since exponents refer to repeated multiplication, exponential functions are often talked about in the context of compounding growth. So if we think about 2 multiplied by 2 multiplied by 2, that continued doubling effect can lead to these really large gains, these really large growth rates. And so for that reason, talking about compounding, no, sorry, try that, give me a sec. I just want to try and Since exponents refer to repeated multiplication, this means that any growth is going to compound. And so for this reason, exponents and exponential functions appear a lot when talking about finance and in particular economics. So we're going to explore one of my favorite economic questions, which is related to the fictional in-game economy of the Kingdom of Hyrule. Now, the Kingdom of Hyrule is the setting of the Legend of Zelda video game franchise, where you play the protagonist Link as you explore the realm and usually try and fight the forces of evil. And on the way, you collect in-game currency in the form of rupees, which you can then exchange for goods. But since the game has been around since its original release 40 years ago, it's been around a long time, we actually have some really interesting data on the value of this in-game economy, on the value of a rupee. And we can understand this using exponents and exponential functions. So I have some rupees on the stage in front of me. And just to get a feel for how they work, we have 6 different colors. So the green rupee is worth 1, has a value of 1 rupee, the green gem. The blue one is going to be 5. We then have the red one, which is worth 20. We have the purple one, which is worth 50. We have the silver one, which is 100. And then the gold, which is 300. Now that in itself is fine. They're just different denominations. But if you consider some of the older games and the initial wallet size, so when you begin your adventure, you have a wallet to contain your rupees. So if we go back to the first one that I played when I was a kid, which was Ocarina of Time on the Game Boy from 1998. So the initial wallet size could hold, the initial wallet could hold 99 rupees. So it might be something like this, right? I could get my 99 rupees in my wallet. However, if you fast forward a few years to Twilight Princess, which was the first Zelda game on the Wii, and again, one that I played when I was much younger. So that came out in 2006. So we've progressed 8 years further forwards in time. But now, your initial wallet size is 300. So that would be a bit more like this. You need something a bit bigger to carry those initial rupees as you progress through your adventure across Hyrule. But then if we go to the next game, so one from 2013 called Link Between Worlds. This was on the 3DS. And in this game, your initial wallet has increased again. And now it's actually 9,999. So now I've got quite a big sack of rupees that I'm carrying over my shoulder on my adventures. And then you go to the most recent game, 2023 and Tears of the Kingdom, the initial wallet size is now 999,999 rupees. Like, I do not have a sack or a wallet big enough to show what that would look like. But this is suggesting an idea that you need more rupees to progress through the game and so to travel around Hyrule. So it's suggesting the economy could be in decline. And we can see this further with the specific items, because just because you can carry more rupees doesn't mean that necessarily prices have gone up. So if we take one of the most famous items in Legend of Zelda and those games, so this is the Hylian Shield. Now, the Hylian Shield, again, going back to Ocarina of Time, had a value of 80. Ah! Okay, should I go from holding the shield?
Yeah, just go from holding the shield to placing it down. We'll be good.
Okay, I just forgot the number. So it goes 80, 200, 3,000. Okay. Now the Hylian Shield in that... now going back to Ocarina of Time in 1998, the Hylian Shield in that game has a cost of 80 rupees. So if I count this out, 80 rupees, and it's going to test my mental arithmetic. So I think if we get 3 of the reds, so they're 20 each, and then we want 4 of the blues. Okay, so I make that 80 rupees. This pile of rupees would buy you the Hylian Shield in Ocarina of Time. But then if we progress to Twilight Princess, so go forwards 8 years or so. So now the Hylian Shield actually costs 200 rupees. So I'm going to need an additional red, and then I'm going to need 2 purple. I'm going to need 2 of those 50s. Right? So you might think, okay, fair enough, few extra rupees, you know, we've gone forward in time, possibly expected. But then if we go to the most recent game, Tears of the Kingdom, the Hylian Shield, if I take all of my rupees, right, so throw an extra couple of purples, that's an extra 100. These are all another 400, they're 300 each, that's another 1,200. And I might as well throw in the 4. But they're kind of useless, because even with all of these rupees, right, I've got almost 2,000 rupees. I don't have enough. The shield costs 3,000 rupees in the latest game. So we've got here, I would say, quite a lot of evidence that the Hyrulean economy really is in decline. But to be sure, we should really look at the maths behind this. And for that, we're going to pop over to the screen and look at those exponential functions. So, what I've got in this table is the most expensive item across all of the Legend of Zelda games. So going right back to 1986 and the original through to the most recent Tears of the Kingdom. And this shows what the item is and its price in rupees. And again, this is the most expensive item in the game, which again feels like a good proxy of the economy. So if we take this data, we can then plot this now on a graph. So if we do so, we've got here on the y-axis the price in rupees, so starting from 0 up to 3,500. And then across the bottom, we've got time. So this is progressing in years, where 0 is going to be the release of that first game. So the beginning of the Hyrulean economy in 1986 through to the present day and the latest game. And again, we see the trend that we've identified now in a couple of situations. So we're seeing that things are more expensive, right? The price is increasing over time. And now if we use our tool from economics, we use our exponential function. So what we use here to model inflation is the following function. So P is our price in rupees, and we model it as P is equal to a constant A multiplied by an exponential E to the power of I times T. So P is just the price, that's giving us the price. T is time, so that's our variable here. And then A and I are the things we need to work out. So A is just going to be the initial value down here. That's our starting point, like what was the price in that first instance. And then I represents this growth rate. So I is going to actually give us the rate of inflation that's occurring in the Kingdom of Hyrule. So if we draw our exponential curve, so this was just done using graph plotting software to fit this particular inflation curve to the data, then the values we get for this shape curve is we get A is equal to 273, so that's just our initial pricing. But then we see here I, that growth rate, is 0.066. So now that's written as a decimal. So if we convert that to a percentage, as usually we talk about inflation as a percentage, then 0.066 multiplied by 100 means that on average, over the last 40 years, Hyrule, the kingdom in The Legend of Zelda, has experienced an average inflation rate of 6.6% per year. Now, for comparison, over the last 40 years, the average inflation rate in the United States has been 2.8%. So I think we can conclude, using our knowledge of exponents and exponential functions, that the Hyrulean economy really is in decline. So it appears we have quite a lot of evidence that the value of the rupee is in decline. Rupees do just not go as far as they used to. But really, we'd like to quantify this, and we can do so by measuring the rate of inflation in the Kingdom of Hyrule. And that's going to require an exponential function. So let's move over to the screen. So in this table, we have listed all of the Zelda games and all of the most expensive items from each of those games. That fine?
Tom, are we taking it through the end to cover the second reference as well?
Oh, sorry, I thought I was just going to do that bit and then redo the end, as opposed to, I apologize, I got confused. I thought I was just doing that as a transition and then the end as an end. I can redo it. I can redo all the slides if you want.
We can try to track it down. It'll probably take about the same amount of time for us to find the cut point.
The cut point is where 6.6% appears at the end, here.
Okay.
But if it's easier for me to redo it, just tell me and I'll redo it. Sorry, I don't want to make it difficult.
No, that's all good. If you want to back up like a little bit from wherever you think it was, I will take you at the TV and we will do that.
Okay.
And we are live, so anytime, Tom.
Okay, thank you. Right. So what we can see here is that the value of inflation, the rate of inflation, is given by 0.066. Now that's a decimal number, and we usually talk about inflation as a percentage. So we have to multiply that by 100 to get that final value of 6.6%. So this means that on average, over the last 40 years, Hyrule has seen a rate of inflation of 6.6%. So I think it would be safe to conclude that the rupee really is in decline, and especially if we compare it to the benchmark that economists talk about. So traditionally, a healthy amount of inflation is around 2%. So we can see here this is much higher, right? Rupees really do not go as far as they used to. In this chapter, we've seen how order of magnitude estimates can help us to get a feel for the scale of the solution to a problem. We then defined exponents as repeated multiplication and looked at some of the rules of exponents through addition, subtraction, and multiplication. We then looked at the inverse of exponentiation in the form of logarithms, and we saw that the laws of logs are really just the rules of exponents in disguise. We also looked at defining both rational and irrational exponents, for example, computing the value of pi to the power pi. And finally, we applied everything that we'd learned about exponential functions to compute the rate of inflation in the fictional kingdom of Hyrule. In the next chapter, we're looking at combinatorics, which means lots of counting, so I'd better get to it.